Hello and welcome to this exam revision webinar for Mathematics 2. My name is Siri Koletsis and I'll be hosting today's presentation. So what I've done for us is I've prepared a set of exam style questions that I'm going to go through and solve live, just like I would in the actual exam. And this will also give us the opportunity to revise many of the key topics in the course. So the first question I've prepared for us here goes as follows. The supply and demand functions for a market are the equations you see here. Qs of p is p over 4 minus 1, and Qd of p is 11 minus 3p over 4. And the first task is to find the equilibrium price and quantity. And as we go along, if you want to take a few notes and jot down a few things, then of course feel free to do that, but we'll move at a relatively swift pace throughout. But you may find that useful just to see and refresh that you know how to approach each question. So we want to find what I call P star here, the equilibrium price. And what we need to solve is Qs of P equals Qt of P. And so this is a relatively straightforward operation here. We can see straight away we send that minus 3 over 4p to the left-hand side. That gives us p on the left-hand side, and then we send the minus 1 there. We add plus 1 to both sides, if you like, and we see immediately that p star equals 12. Now we just need to substitute that back into either equation 1 or 2, if I give them a number here, to find Q star. And let's say that I use the supply equation. So Q star is Qs of P star and so we see here that the equilibrium quantity is 2. In other words, if we sketch the graphs for the supply and demand equations, then this is the intersection point. Q star is 2 and P star is 12. Now moving on to part B of the question. The government imposes an excise or per unit tax of tea on the market. Find the new equilibrium price and quantity. And then also answer what percentage of the tax per unit has been passed on to the consumer. So take a moment to think about what changes now that we have the excise tax. Suppliers now see an effective price of P minus T. And I'm writing that down here also because we're doing revision. Of course, you could now just write down the new supply equation directly. So let me call that Q with an underscore there, T S of P. Well, that is QS, where the argument now is P minus T instead of P. And remember that our supply equation was Q equals P over 4 minus 1. And so now we get P minus T over 4 minus 1. Now the consumers, they still see a price of P, and so the demand equation is unchanged. And like I said, since we're doing revision here, I'm writing a little bit extra. It's a good idea to do that when you're revising. But of course, in the exam, you can condense this down, right? So just write down what you're solving, the new supply equation and the demand equation, which stays unchanged. Solve these to set these equal to each other and solve to find the new equilibrium point. But let's make it very clear here. The new demand equation is just the old demand equation. And then, as we said, we find the new equilibrium price now. Just like we did in part A by equating these two expressions for Q. So let me call this PT star. In other words, we need to solve this equation. So first thing I can do here, I can multiply both sides of the equation by 4 to get rid of the fractions. Then this is our new left-hand side. And this is our new right-hand side. And now we just need to bring it all together. If I collate all the p's on the left, then we'll see that we have 4p. And then we get 48 plus t on the right-hand side. And now we just divide out by 4. And we are done. So our new equilibrium price in the presence of tax is 12 plus t over 4. And now we need to substitute that back into either the new supply equation or the demand equation to find Qt star. And I'm going to use the demand function. Sometimes the advice here when there's an excise tax is to use the demand function because it hasn't changed. You could, of course, use the new supply function, just need to make sure that you indeed then use the right one, that it's Q equals P minus T over 4 minus 1 if you use the supply equation. But then the demand function hasn't changed. Either way, we're going to get the same answer. So we just plug in our PT star here into the demand equation. And then we just need to pull all of this together. And we see that we have 2 minus 3t over 16. Now, that answers the first part here, find the new equilibrium price and quantity. And now we want to answer what percentage of the tax per unit has been passed on to the consumer. So let's just look at how the price changed when we introduced the the excise tax. So the new price was 12 plus T over 4. The old price was 12. So the difference in price is T over 4, which means that 25% of T has been passed on to the consumer. Should write the tax really. Okay. So now let's move to, no, we have one more part. I thought we were done, but we are not. Write down an expression for the government's tax revenue. What value of tax will maximize this revenue? So have a think about what this expression for the tax revenue will be. While I'm just writing here, I'm going to call that RT. And how much does the government get? Well, for the quantity sold here, our equilibrium quantity, we multiply that by T, it gets that per unit. So we see here that the expression for the government's tax revenue is a quadratic in T. And we want to argue what value of T will maximize this revenue. And so let's find the critical point of this quadratic. And that happens when the first derivative of R is equal to 0. And so we differentiate. So it's 6t over 16 here, but that simplifies to 3t over 8. And now we just make t the subject here. And we see that the single point, stationary point or critical point as we call it, of the revenue function is t equals 16 over 3. But we want to make sure to argue that it is a maximum, and not only a local maximum, but of course a global maximum. Now we know what the shape of the graph of the revenue function is. Of course, it's a quadratic and upside down parabola like this. But let's find the second derivative here to argue. A second derivative here is negative. Sorry, the second derivative function is just the constant minus 3 over 8. Was getting a bit ahead of myself there. So the second derivative evaluated at the critical point is, of course, also negative. It doesn't change. And this means that the critical point we found is a local maximum. So several ways now to argue that it's also the global maximum. I'm going to say, since it's the only critical point. It is a global maximum. And that brings us to the end of question 1. Now then to a matrix question and a system of simultaneous equations. We are told here to use row operations to determine the value of the constant k, if any, for which the system of equations we see here has no solution, a unique solution, or infinitely many solutions. And it says for the value of k you found in part 3, write the solution in vector form. So we know already that at least this system can definitely admit infinitely many solutions. Now we are going to use row operations. So let's just remind ourselves what this system here of equations looks like in matrix form. Of course, in the exam, you would go straight to the augmented matrix and then start doing row operations to save time. But since we're doing revision, let's make it very clear. Okay, so we have the so-called coefficient matrix. That's going to be a 3x3 matrix here. Then we have the vector of unknowns. And then we have the right-hand side. Like this. Now I've already written down 1, 2, 0 here as our first row. What is that? Let me see if I can just, can I circle? Wanted to see if I can highlight here. Anyway, new upgrade I'm not that familiar with. Just take the coefficients of x, y, and z here in row 1 and put them as row 1 in the matrix. And then the right-hand side 3, there is the first entry of our vector b. Now, similarly then, the second row is 3, 6, 3, and then we have 21 on the right-hand side, and then we get 2, 4. And here comes this k here as the third entry of the third row. Now we're ready to start our answer. But if I wanted to give this a name here, the coefficient matrix, let's call it A, then we have vector x of unknowns and the vector b on the right-hand side. But like I said, in the exam, we would effectively start here. Just write down the augmented matrix straight away. Just take care to transfer all the numbers correctly, like this. And so we want to analyze this system here. And that means that we want to aim for echelon form. Now we see here that we already have a so-called leading one in the first row here. And so what we want to do now is we want to create zeros below that leading one. And that's what determines my choice of row operations. There are many possible ways of going at this, but this is the most, if you like, algorithmic method. Create leading zeros below your leading ones. So row 2, we see that if row 2 goes to row 2 minus 3 times row 1, well, then that 3 in the first 3 there in the second row will become 0. And for row 3, we see that if we do row 3 minus 2 times row 1, well, then that 2 will become 0. And then the rest of the row will become whatever it becomes. So we keep row 1 fixed. And in this case, we're only subtracting multiples of row 1 from the other rows. So I might as well write down row 1 first, since it's not going to change. Now let's just do the row operation, see what the result is. Row 2 minus 3 times row 1. We already know that this will become 0. That was by design. And then we have 6 times 6 minus 3 times 2. Well, that will give us 0. 3 minus 3 times 0 just leaves us with 3. 21 minus 3 times 3, that is 12. And then row 3 here, again by design, we get 0 here. 4 minus 2 times 2, well, again, that gives us a 0. Then we have k minus 0 times 2, well, that just leaves us k. And then 6 minus 2 times 3, well, that gives us 0. Okay, now I would like to make this 3 here in the second row into a leading 1. So let's just divide row 2 by 3. Or multiply by a third. And notice here that, of course, I'm writing arrows here because these matrices are obviously not the same. We are changing the matrices. We're doing row operations, which means that we are changing some of the equations in the original system. We'll talk about that at the end, just what that means. Okay, so this is our new row 2. And now we see that we have a leading 1 in row 2, like we wanted. And now we want to create a 0 below that second leading 1. And so if row 3 goes to row 3 minus k times row 2, then that will achieve our aim. Rows 1 and 2 don't change here. And we get minus 4k there on the right-hand side. And now we are ready to start analyzing and answer these questions. So have a little head start to think about, are there any values of k? So we're looking now at the reduced here, augmented matrix. Are there any values of k for which this system has no solution? Have a think about it. So looking at the last row, we have 0, 0, 0 in the coefficient matrix part here. And then we have this minus 4k. When would that correspond to something, to a system of equations here that has no solution? Well, if k isn't 0, then we have something non-zero on the right-hand side. That would correspond to the equation 0x plus 0y plus 0z equals something non-zero. And there aren't any values of x, y, and z that can ever satisfy that. So if this minus 4k here is not equal to 0, which is the same as to say that if k isn't equal to 0, well, then this system has no solution. Now, how about a unique solution? Is this possible? Is there a value of k that would make this system have a unique solution? Have a think about it. You know systems with a unique solution very well from Mathematics 1, because that was all we covered in that course. Is there any value of k that can satisfy that? The answer to that is no, there isn't, because you see here that there's no value of k that would give us 3 leading ones here in the reduced coefficient matrix here. So in this part here. So for this system of equation, that's not possible. So let's write that down. So we cannot get 3 leading ones. In a reduced row echelon form of A. Another way of saying that is that A is not invertible for any value of K. This matrix A here that we started with. And finally, we know that there is a yes answer to part 3, because it says here that for the value of k we found in part 3, write the solution in vector form. So let's see what this value of k is, and then we'll write it out. Write out the solution in vector form, that is. And so again, we look at this reduced augmented matrix, and we know we answered in part A when there was no solution. So in order to have a solution then, well, the last row here, the entire row has to be zeros. So that would be equivalent to an equation of 0x plus 0y plus 0z equals 0. And that's all fine. That's basically just showing us that there was one equation in the original system for that value of k, which we see is going to be 0, that was redundant. It doesn't give us any more information than the first 2 equations. So let's write this down. So if minus 4k equals 0, i.e. if k equals 0. And then let's write out what our reduced augmented matrix becomes, so that we can see it clearly before we write out then the solution in vector form. And if you're working, go ahead and take a head start on writing out the solution in vector form, so that you can see if you are confident with that at this stage of your revision. And if not, then let's fix that today. That is also fine. Let's make sure that we know how to do this. I like to circle my leading ones. And so we see here that the column here that's missing a leading 1, well, that's column 2. And so y here can be treated as a so-called free parameter. And so we like then to let y equal some letter, let's say s, where s is, just going to use this sign here, r, for the real numbers. S is any real number. Now I also want to just write out in equation form then what we have here. The first row tells us that x plus 2y equals 3, but y equals s. So we have x plus 2s equals 3. The second row tells us that z equals 4, doesn't depend on y or s in this case at all. And that is our system. And now we just arrange this for x, y, and z. So looking at the first equation, let's make x the subject. That means that x equals 3 minus 2s. I'm not going to write it there, but you could have done it. I'm just going to write that now straight into my vector. Y is just s, and z is just 4. Now we can go one step further and separate this into a point here that doesn't involve s. Plus a so-called direction vector here that multiplies s. And so this is our final answer to part 3. So that's the solution in vector form when k equals 0. And just quickly, like as I mentioned while I was solving it, it's just a little bit as an aside really. What are we doing here? We said, well, we started with this simultaneous system of simultaneous equations. In matrix form, we wrote it out like this, and then we created the augmented matrix, and then we did elementary row operations on that augmented matrix, which is why we wrote arrows here, because obviously now the matrix changed. And so we are basically changing the equations. Well, we didn't change equation 1, but equation 2 changed entirely and just became z equals 4, right? And then the third equation, well, that depended on the value of k. So what does that mean? What have we done? So this final system, let's say this final system here, when k was 0, x plus 2y equals 3 and z equals 4, is obviously not the same as the original one, but what they have in common is that they have the same set of solutions. So they have the same, if it's a unique solution, then they have the same intersection point. If it's infinitely many solutions like here, well, there's a line of solutions, well, that's what they have in common. So if we go to, we don't need to visualize in this course, but if you go to R2 for a moment and think of where you have two equations and two unknowns, for instance, and they represent lines in R2, well, something that represents solution here, the no solution like we talked about in part 1, well, that would be two parallel lines, right? So basically then they are the same equation. One equation would just be the multiple, a non-zero multiple of the other equation. And so if you put those equations into an augmented matrix and did row operations, you would get something with 0, 0, non-zero as your second row. And that would just tell us this, those lines never intersect. They have no common point. Now, if we had a unique solutions for two lines in R2, well, then you know that they would certainly not be parallel and they wouldn't be the same line. So they would cross in a single point. And then finally, the last situation here, when could two lines in R2, if we have two equations for a line in R2 and have infinitely many solutions, well then the second equation, so I said it wrong for part one. That's when the second equation would be a multiple of the first equation. It would just be the same equation, the same non-zero multiple of the first equation. So that would represent the same line. So that's not the case for case one. Then you get a 0, 0, non-zero if you do row operation. So you could test that. You could just write down 3 cases in R2, and then that's all we are also doing here. Just geometrically, it's a different representation. Now, let us move on to the method of Lagrange multipliers. You know this very well from Maths 1. And here we've just expanded to a third variable here. So this question reads, for x, y, and z all strictly greater than 0, use the method of Lagrange multipliers to find the values of x, y, and z that maximize the function x cubed y squared z, subject to the constraint that x plus y plus z must equal m, and m is a positive constant. So have a think about, just again, a head start at this point in your revision to write down the Lagrangian. So Lagrangian is a function of x, y, z, and lambda. And we start by writing down the function we are optimizing. In this case, we are maximizing. And we know that that is this expression here, x cubed y squared z. And then we write minus lambda. We arrange this constraint here in the form x plus y plus z minus m equals 0. And then we take that left-hand side, we put it in here. So that's the Lagrangian. I also like to write down in general terms what we now need to solve, the so-called first order conditions. And so we need to find all the first order partial derivatives of the Lagrangian. In general, these are functions of x, y, z, and lambda, and then we set them equal to 0. I like this shorthand here where I just write L and then a subscript x for the partial derivative of L with respect to x. So similarly now, we have the other first order partial derivatives of the Lagrangian. So this is the simultaneous system we need to solve. In other words, we're just finding critical points of the Lagrangian. And so basically here we just need to be on top of our differentiating skills. Now, starting with Lx here, we treat y, z, and lambda as constants. And so looking at the Lagrangian here, well, this y squared z is going to be treated as a constant. 3 and x cubed comes down, the new power becomes 2. So that's the first term of the Lagrangian differentiated with respect to x. Then we look at the rest here. What do we have that involves x here? We have minus lambda x. The rest here is just treated as constant, so differentiated with respect to x, we get minus lambda, and then we set that equal to 0. So that is the first equation in our simultaneous system. Moving on to differentiating L with respect to y, we now treat x, z, and lambda as constants. So looking at the first term here, well, the power here 2 is going to come down. So y squared here, that part will be 2y. And then we just keep x cubed and z because they're treated as constants. Now let me put the 2 though in front and just think it's neater like that. Now we have y and then z. Again, what do we have left involving y? We have minus lambda times y. So partially differentiated here with respect to y, get minus lambda, and then we set that equal to 0. Now, differentiating partially with respect to z, well, what multiplies z here involving x and y is treated as a constant, so x cubed y squared is the partial derivative of x cubed y squared z with respect to z, and then we have minus lambda z left here, so differentiated with respect to z, we get minus lambda, and then we set that equal to 0. That is our third equation, and then finally we need to differentiate the Lagrangian with respect to z. First term here, differentiate with respect to lambda, sorry. First term doesn't have any lambdas in it, so that's going to vanish when it's differentiated with respect to lambda. It's treated as a constant. And then we have minus, and then the whole thing, expression there in the brackets left. So we could just write it like this. Of course, this fourth equation here, multiply both sides by -1 to get rid of the minus sign and send that minus m to the right-hand side. We have just recovered the constraint we started with. So this is equivalent here, which is easier to work with later when we're going to substitute here into equation 4, but we'll get to that soon. Now, what do we want to do next? We want to eliminate lambda from equations 1, 2, and 3. And it's worth writing that down, I think. It makes it very clear what you are about to do here. So often, I know that students don't like to write words when you're doing maths, but it's worth writing a few words so that you remind yourself what you are doing. So I think that's worth trying if you haven't already. Okay, so I'm not going to write it out here. I could, I'm just going to save some space. But if we make lambda the subject here of equation 1, well, just we add plus lambda to both sides, or if you like, send minus lambda to the other side, you get lambda equals 3x squared y squared z. Similarly here, equation 2, then becomes lambda equals 2x cubed yz. And the third equation becomes lambda equals x cubed y squared. So we can now equate these three expressions for lambda. Now, I want to simplify this. Let me note here, I've been told in the question that x, y, and z are positive, and well, they're non-zero, and I can certainly divide as I please to simplify. Let me just point that out here. And what would it be good to divide by here? Well, I can take an x squared, divide by x squared in each of the three equations, and also y. And let's see what that gives us. First equation becomes 3yz. Second equation becomes 2xz. And the third equation becomes xy. And now this equates here to two independent equations. So I can set, say, the first equation equal to the third equation and the second equation equal to the third equation. And now we want to simplify that further. For the first one, then here, I see that, well, I can divide by y throughout. Remember, we said y is positive, was given in the question. So let me just point that out. So we get that 3y equals x. And over here, well, x is greater than 0, so we can divide by x throughout. And so we get that 2z equals y. Now, so that's what happens when we eliminate lambda from equations 1, 2, and 3, we get a relationship here between x, y, and z that we can use to substitute into equation 4, and equation 4 will now become an equation in only one variable. So both of these here will be substituted into equation 4. Right, so x, sorry, so I have said I've written down the wrong, it should be 3z equals x here. Now, x is 3z. Y is 2z. And so we can now solve for z. So the value of z that maximizes the given expression subject to the constraint is m/6, where m is a positive constant as given in the question. So notice here, of course, these values at the critical points where we have optimized the function subject to the constraint, well, they are functions of m because we haven't specified what m is. But remember to think of m as given here. So we're just solving it for any positive constant m. So with that, we can now use the expressions we derived above to find xz, x star, and y star. Y star is 2 times z star. That is the final answer. Notice is we're only asked here to find the values of x, y, and z that maximize the function x cubed y squared z subject to the constraint that x plus y plus m, x plus y plus z equals m. We weren't asked to find the value of the function at the maximum, but a question in the exam may ask you to do that. So then you just evaluate the expression for the function we are optimizing at the values x star, y star, and z star. Now we have a differential equation here. Suppose consumers anticipate market trends according to the demand function that QD of P of T equals 8 minus 2P of T minus 2P prime of T plus P double prime of T. And the supply function is QS of P equals P minus 1. Use the condition for equilibrium to find P of T given that P of 0 equals 1 and P prime of 0 equals 2. And then describe the behavior of P of T as T increases. Well, let's start here. We started this revision with finding equilibrium points. So we know that at equilibrium, we have QD of P of T equals QS of P of T. So let's write out what we get. And then let's write it in the more standard form, starting with the second derivative here. P double prime of T minus 2P prime of T minus 3P of T. And then we can put the constant on the right-hand side. So let me just call that a star here. We'll refer to this equation later. So we have a second order non-homogeneous differential equation here. And now we want to solve that. Start by finding the roots of the so-called auxiliary equation. Take a head start to write down the auxiliary equation. We have m squared minus 2m minus 3 equals 0. And so we can either factorize directly here, or we can use the formula for the solutions of a quadratic equation. But you may notice here that this factorizes into m minus 3 times m plus 1. And so the two roots are 3 and minus 1. And that means that the so-called complementary function well, I'll give you a head start. P of t equals a times e to the r1t, so here 3t plus b times e to the r2t, in this case minus e to the minus t, where r and b are arbitrary constants. So that was a complementary function. Now we need a particular solution. And since the right-hand side here is a constant, we try P of t equals c, where c is a constant. Well, if P of t is c, then both the first and second derivatives are 0. And then we plug those back into the differential equation that we start there. minus 3c is minus 9, so c. So c equals 3, and therefore our function is p of t equals 3. Now we've learned then that the general solution is simply the complementary function plus the particular solution. Let's call this equation a double star, something like that. And again, A, B are arbitrary constants. Now, in order to determine A and B, we need the so-called initial conditions, and those are given here in the question. P of 0 equals 1 and P prime of 0 equals 2. So we are going to need P prime of t, and so let's differentiate P of t here as a first step, and then we'll use P of 0 equals t and P prime of 0 equals 2 to find the values of A and B. So that's P prime of t. Let me give that a 3-star here, just so that when we're referring to it later, it's clear. So now, applying then P of 0 equals 1 in equation with 2 stars here. Let's see what we get. Get 1 equals A plus B plus 3. In other words, A plus B equals minus 2. So that's the first equation in the system. And then using P prime of 0 equals 2 in our equation here, with 3 stars above the P prime of t expression. We get the second equation in our simultaneous system. And you know, there are many ways to solve this here. I mean, we could even use the matrix method if we wanted to with A and B as our unknowns, but we won't do that here, but good to do for practice. Now we can see here that if we add equations 1 and 2, we'll get B minus B. So the B's vanish and we get our solution for A. we get 4a equals 0. And so a equals 0. Which we just substitute into either 1 or 2. To see that b is -2. So this here answers the first part of the question. So we've now found P of t here, given the initial conditions. And then we just want to answer also the second part, describe the behavior of P of t as t increases. And you may find it useful here when you analyze to rewrite this as follows. Just remind yourselves that e to the minus t is the same as 1 over e to the t. Just putting that in brackets here. So as t increases, minus 2 e to the minus t increases to 0, which means that P of t increases to 3. As t increases. Another way to see it is that, so think as t increases here, the denominator here gets bigger and bigger. So you are deducting something from 3 that you're deducting less and less. And so you come from underneath and we increase up to 3. Now, some diagonalization to end with. Find the eigenvalues of the 2 by 2 matrix A here and an eigenvector corresponding to each eigenvalue. Hence find an invertible matrix P and a diagonal matrix D such that A equals P D inverse. And as you know, we start by finding the eigenvalues. And to do that, we find the determinant of the matrix A minus lambda times the 2 by 2 identity matrix equals 0. And so A minus lambda times the 2 by 2 identity matrix, well, that we can write as follows. We just deduct lambda on the diagonal of A. just give me one moment here. I just need to plug in my computer. So just have a go ahead and solve this. Set this up. Okay, that's all done. I thought the laptop would last me the battery, but it didn't. Okay, so pulling this together then, we see that we have lambda squared minus 5 lambda plus 6 equals 0. And again, we solve that either by using the formula, or you may have spotted that this factorizes as follows. And so our two eigenvalues are 2 and 3 respectively. Doesn't matter what we call lambda 1 and what we call lambda 2, that's up to you. So these are our eigenvalues. Now it's worth refreshing here. What does an eigenvector x satisfy? A times x equals lambda x, where first of all, x is not the zero vector, and lambda here is just some real number. In other words, an eigenvector x is a non-zero vector that is simply stretched by the matrix A by a factor of lambda. And now we want to find an eigenvector corresponding to each eigenvalue. So let's start with lambda 1 equals 2. And what we need to solve is A minus 2 times the identity matrix times x equals the zero vector. And so deducting 2 from the diagonal of A, it's useful to write down those two entries first. The other two entries stay the same. And here we are in the situation here that I talked about earlier. So in R2, minus x plus y equals 0, minus 2x plus 2y equals 0. So that simultaneous system of equations, oh, you see that the second equation is just a non-zero scalar multiple of the first. So these equations represent the same line. And so one of these equations is redundant. If we put this here into an augmented matrix and row reduce, the second row will become all zeros. And that means that we can drop one of the equations and just keep one. So minus x plus y equals 0. It's the same as saying that y equals x. And so we can take our eigenvector, let me call it v1 since it corresponds to lambda 1. Any non-zero vector whose x and y entries here are equal will do the job. So there are infinitely many possibilities. This is by no means a unique answer is unique up to that scalar changing. And how do we know that we have the right answer? And of course, you should do this as you're revising and also in the exam. A times 1, 1 has to give us what? 2, 2, because 2, 2 is 2 times 1, 1. And we know that A should stretch this eigenvector here, 1, 1, by a factor of 2. So it's easy to check our answer. So for lambda 2 equals 3, we now do exactly the same thing here. A minus 3 times the identity matrix times the vector xy equals the 0 vector. We write that out in equation form, deducting now 3 on the diagonal of A, keeping the off-diagonal entries the same. And now it's even clearer. The second equation, or the second row here, is just 1 times the first equation, but it's the same principle. It's a non-zero scalar multiple of the first. So we can keep just one equation here. And so any non-zero vector where the second entry is 2 times the first entry is an eigenvector of eigenvalue 3. Again, very easy to check. A times this vector 1, 2 has to give us back 3 times the vector 1, 2. And then now to finally then answer the question. So with P equals the following, and we will talk about how these are constructed. And D as follows, we have that A is the product P, D, P inverse. Notice here in the question, we are not asked to find P inverse, so we don't need to spend time on that. Now, what's important here in the construction? Again, the choice of P and D are not unique. So notice that I put eigenvector v1 as the first column of P. So that's why I'm writing it like that here, just underlining to show it's the vector v1. And my second column of P, well, that's the eigenvector v2. Once we have committed to that ordering of the eigenvectors, we have absolutely no choice, no freedom, that is, in how we write D. The diagonal matrix D has to have the eigenvalue lambda 1 corresponding to V1 as the first entry here, and lambda 2, which corresponds to V2 as a second entry on the diagonal there. But we could also choose the opposite ordering. So let me call that, say, P dash. If I put V2 first and then V1, well then, you know what I'm going to say. We have to have now lambda 2 first and then lambda 1. And if you're not convinced, you can find P inverse and P dash inverse and multiply out PD P inverse in each case, and you will see that you're going to recover A. So that ordering, once you've committed to the ordering of the eigenvalues, well, then you have no freedom in how you select D. Now, use your result from A to find sequences xt and yt such that this system here of sequences xt equals xt minus 1 plus yt minus 1 and yt equals minus 2xt minus 1 plus 4yt minus 1. And then we have that x0 equals 4 and y0 equals 3. So just remember that we had a equals 1, 1, minus 2, 4 here. So you can see here that our system of sequences here, where we have xt here, is the vector xt, yt. This system that we have above is simply a times x t minus 1. And now we're going to use the diagonalized form of A that we found. And now we let xt equal p times ut. Then we have that ut equals p minus 1 xt. So ut is d times ut minus 1, where d now is that diagonal matrix we found in part A. And now we see that we have uncoupled these, so that ut is just 2 times ut minus 1. And the sequence vt equals 3 times t minus 1. And these we know how to solve. And again, writing down the auxiliary equation here for both. we have that ut equals a times 2 to the t, and vt equals b times 3 to the t, where a and b are arbitrary constants. And now we go back to xt by using the xt is p times ut, where again p is the matrix we found in part A. And then finally, we use x0 equals 4 and y0 equals 3 to find a and b. We get that b is minus 1 and a equals 5. And so now we can write out the sequences xt and yt. And that is our final answer. And that brings us to the end of this presentation. So I hope you found it useful to go through and solve these exam style questions in a similar fashion to what I would do in an exam. Of course, we've sprinkled this with a little bit of extra commentary for revision purposes. So remember in the exam that you can answer the questions in any order, just and move on. If a question takes too long, you can always come back to it later. Remember to show all your working. There are plenty of so-called method marks available. What the examiner wants to see is that you know the methods and the technique to solve each question. Of course, numerical accuracy is also important, so do practice that to get in top form now in the weeks leading up to the exam. And if you make a mistake, remember you can just draw a line through it and continue below. So with that, I want to wish you a productive revision period and good luck with all your exams. I hope you've enjoyed the course, and I wish you all the best in your continued studies here with us at LSE and the University of London and all your future endeavors. So thanks again for joining today.